Welcome to the series on polymer properties. Today's topic is polymer crystallization. Crystallization is a very important property of a polymer, as many of the physical properties of polymers depends on their crystallinity. This video will provide brief overview on fundamental concepts of crystallization, factors affecting polymer crystallinity, experimental methods to determine crystallinity, and polymer properties affected by its crystallinity. Polymers are an integral part of our lives. Every day we use many polymeric products, but we never realize that how and why these polymeric products are different from each other. Some things are transparent, opaque, like water bottle, milk containers, etc. Whereas other polymeric products like table, chairs, swings are strong. So what makes polymers transparent, opaque, or strong? Among the many factors that influence polymer properties, polymer crystallinity is one of them. Depending on the degree of crystallinity, polymers can be transparent, translucent, opaque, strong, or weak. How much crystalline polymer would be, that depends on tendency of a polymeric chain to make crystals. Those who make crystals are called crystalline or semi-crystalline polymer, and those who do not make crystals are called amorphous polymers. In amorphous polymers, polymeric chains have random orientation with very irregular structure. A perfect example to visualize amorphous polymer is boiled noodles. The way noodles are physically entangled and loosely bound to each other, polymeric chains in amorphous polymers are also present in the similar fashion. These polymers do not make crystals. Even if they make crystals, their crystallinity is very low, and that is why these polymers are transparent in nature. Whereas semi-crystalline polymers have both randomly oriented chains as well as highly ordered structure, where polymeric chains arrange in a very specific pattern to make a shape. These specific shapes are called crystals, and the process of formation of crystal is called crystallization. If all the polymeric chains are involved in crystal formation, such polymers are called crystalline polymers. But in reality, no polymer is 100% crystalline. Most of the polymers are semi-crystalline in nature. Now the question is, how do chains form ordered structure, or how do crystals form, and why do not all the chains participate in crystal formation? Suppose here we have polymer in melt state, where polymeric chains are randomly oriented and there is no crystal. So thermodynamically, the best situation to form crystal is that all the chains line up straight parallel to each other. But this structure is possible only in one condition, when all the chains are very short. Suppose all the chains are 10 carbon atom long. In this case, it is possible that all the chain may line up, stretch out and form this kind of structure. But remember that here we are dealing with polymers. Polymers are macromolecules. One chain of a polymer contains few hundreds to few thousands of repeat units. In that case, it's almost impossible for polymeric chains to line up, stretch out. So, instead of forming this kind of structure, polymeric chains forms folded chain structure. Due to very long chain length, these chains exist as entangled or coiled chains in polymer melt. Some part of it is straight and some part of it is part of entanglement or curve. To form folded chain structure, polymeric chains stretch out for some distance. As it encountered any entangled or curved part, the chain folds back. The chains keep folding back and forth to form tightly packed folded chain structure. Straight part of the chain participate in crystal formation, whereas entangled, coiled or curved part creates amorphous region. Chain ends also do not participate in crystal formation because those are physically and chemically very different from the rest of the chain. Now, this packed folded chain structure may contain one chain or more than one. It depends on flexibility of chain. If the chain is flexible enough to re-enter in the same crystal, it can, otherwise it can go to another crystal. Finally, the packed folded structure is stacked together and form a new structure called lamella. Lamella is a fundamental structure of a polymer crystal. These lamella grow radially and form a spherical shape called spherulite. Spherulites are three-dimensional crystal and their size range from few micrometer to 1 centimeter. In spherulite, the lamellas are joined together by amorphous region which provides flexibility to the spherulite or crystal, whereas crystalline region make them strong. Now, let's see what are the conditions that favor crystal formation. Polymers can be crystallized under three conditions. First, when polymer melt is cooled. Second, when polymers are stretched. And third, on solvent evaporation. In melt crystallization, when polymer melt is cooled, during the cooling, polymer form crystal, and this process is called melt crystallization. There are two types of melt crystallization, homogeneous and heterogeneous. Homogeneous crystallization initiates due to thermal gradient in the polymer melt. Thermal gradient tells you about where and in which direction the temperature is fluctuating. Since in polymer melt there are entangled and coiled chains, so temperature around these areas changes frequently compared to rest of the melt. And these entangled and coiled chains act as nuclei and chains starts to attach on them and form crystals. Whereas heterogeneous crystallization occurs in presence of foreign particles. It can be dust particle or additive added to polymer to modify their properties. In this case, these particles act as pre-existing nuclei and crystals starts to grow on them. Crystals formed by this process are usually small because thousands of nuclei are already exist in the melt and all the crystal starts to grow at the same time. On the contrary, in case of homogeneous crystallization, nuclei form from the melt, therefore bigger and less number of crystals form during the process. In case of stress-induced crystallization, a polymer is stressed while its temperature is kept above its glass transition temperature. During the stretching, entangled and coiled chains present in amorphous region of the polymer starts to unfold and align in ordered structure. Using this method, amorphous polymers can be transformed to semi-crystalline polymers. Polymers can also be crystallized on solvent evaporation. This process depends on degree of dilution. In dilute solution, the molecular chains are separated from each other due to presence of solvent molecules between the chains. Thus, these chains exist as an individual coiled polymer chain in the solution. Since evaporation takes place at high temperature, chains have sufficient mobility. With increasing concentration on evaporation, interaction between polymeric chains increases and therefore chain starts to form crystals. This method may result in highest degree of polymer crystallinity. Now let's try to understand why is it that some polymers are highly crystalline and some polymers are highly amorphous. What are the factors that facilitate or hinder crystallization process? Polymer structure is one of the most important factors because different polymers have different structures. Like some polymers are linear, some are branched, some has small side groups, some has bulky side groups. So, to understand the effect of these factors, we need to first understand packing of polymeric chains. Suppose we have two boxes and we need to fill identical objects in one box and different objects in other box. Now, which box will have highest number of objects? Obviously, the box with identical objects. Why? Because identical objects can be arranged nicely. In the same way, polymeric chains who can pack in a crystal nicely form crystalline polymers and those who cannot form amorphous polymers. Now, if we have two polymers, one with linear structure and other with branched structure, Linear polymer can pack well as compared to branched structure. Therefore, linear polymer will be more crystalline than branched polymer. Similarly, if we have two polymers, one with a small side group or side chain and other with bulky side group or big chain. Polymer with a small side group or side chain will pack better compared to bulky side group or big chain polymer. Therefore, crystallinity will be higher for a small side group or a small side chain polymer. Crystallinity is also favored by strong intermolecular forces. The presence of polar and hydrogen bonding groups favors crystallinity because these makes possible dipole-dipole and hydrogen bonding intermolecular force. For example, in case of nylon. In nylon, the polar amide groups in the backbone are strongly attached to each other due to hydrogen bonding, and therefore nylon is a very highly crystalline polymer. Intermolecular force also increase glass transition temperature and melting point of the polymer. The degree of crystallinity also depends on arrangement of side groups on polymer backbone. That is also called as tacticity. If all the side groups are attached on left or right side of chain backbone, polymer is called isotactic. If side groups are alternatively arranged in chain backbone, it's syndiotactic polymer, and if side groups are randomly arranged in polymer backbone, the polymer is called as atactic polymer. Isotactic polymers are usually more crystalline than syndiotactic polymers due to better packing of chains. Atactic polymers do not form crystals due to random arrangement of side groups which do not allow packing of polymeric chains. Cooling rates also show significant effect on crystallinity. When polymers are processed industrially, polymers are often cooled from melt. During cooling, polymer generates crystallinity. If the cooling rate is very high, polymer doesn't get enough time to crystallize at its crystallization temperature because melt starts to cool fast. If cooling rate is too low, polymer needs longer time to crystallize. Also, formation of stable nuclei at high temperature is also very critical. Therefore, an optimum cooling temperature is required to crystallize polymers completely. Annealing is performed above glass transition and below melting point of a polymer to create higher degree of crystallinity. In this process, polymers are kept isothermally. Due to high temperature, polymer chains have sufficient mobility to form a crystal or become a part of other crystal. This process leads to formation of bigger and thicker crystals. For example, in these images we can see that initially polymer crystals have a small size, and after annealing at 180 degrees Celsius for 5 minutes, the crystal size increased, which led to increase in degree of crystallization. Nucleating agents are often added to polymer matrix to modify their properties. Adding nucleating agent to polymers provide a surface to start the crystal growth. Basically, these nucleating agents or fillers act as pre-existing nuclei in polymer melt, which leads to faster crystal formation. For example, here cellulose nanocrystals were added in PLA matrix. PLA is an amorphous polymer with very low degree of crystallinity. The degree of crystallinity of PLA increased in presence of these crystals because these fillers provided surface for polymer chain to form crystals. Since thousands of nuclei started to grow all together, therefore crystallization occurs very fast. Polymer crystallization in presence of nucleating agent or reinforcing filler is also known as heterogeneous crystallization. Plasticizers always reduce polymer crystallinity because plasticizer reduce or weaken intermolecular force between the chains, which reduces chain packing. Now let's see what are the experimental methods to determine degree of crystallinity. There are two common techniques to measure degree of crystallinity, DSC and XRD. Differential scanning calorimetry or DSC measures the amount of energy absorbed or released by a sample when it is heated or cooled. Since glass transition and melting is an energy absorbing process, therefore these appears as an endotherm. whereas crystallization is an exothermic process, so crystallization appears as an exothermic peak. The heat or energy required to melt the crystals is known as heat of fusion, and heat of fusion is used to calculate degree of crystallinity of polymer. Suppose for a given polymer, heat of fusion is 141 joule per gram and heat of fusion for 100% crystalline polymer is 290 joule per gram. Then the percent crystallinity of this polymer would be 49%. Since in reality no polymer is 100% crystalline, therefore heat of fusion for 100% crystalline polymer is always taken from literature. X-ray diffraction technique is also a very common technique to calculate crystallinity of polymers. XRD spectrum of a polymer gives two types of peaks: sharp peaks from crystalline region and broad peaks from amorphous region. If a polymer is highly crystalline, it gives sharp peaks. If a polymer is amorphous, it gives a broad hump or a broad peak. In case of semi-crystalline polymer, both sharp and broad peaks appear in their spectrums. To calculate crystallinity of semi-crystalline polymers, first amorphous and crystalline peaks are separated from the spectrum. Then the area under the crystalline peak and amorphous peak is calculated. The crystallinity is calculated by dividing the total area under crystalline peak by the total area under the diffraction curve, means total area of crystalline plus amorphous peaks. Now let's discuss the effect of crystallinity on optical, thermal and mechanical properties of polymer. Optical properties: generally semi-crystalline polymers are translucent and opaque, whereas amorphous polymers are transparent. In case of semi-crystalline polymers, crystals act as scattering center and thus they scatter the light or reflect the light. Since light cannot pass through the crystal, therefore semi-crystalline polymers are opaque, whereas amorphous polymers allow light to pass and therefore are transparent. Thermal properties: semi-crystalline polymer possess higher Tg as compared to amorphous polymers because crystals act as physical crosslink, which restricts chain mobility and also reduces free volume. Therefore, with increasing crystallinity, Tg of a polymer increases. Crystallinity also increases thermal stability of polymer because more energy is required to melt the crystals. Therefore, thermal stability of polymer increases with increasing crystallinity. Mechanical properties: generally semi-crystalline polymers have higher modulus, higher strength but low elongation at break as compared to amorphous polymers. They have high modulus because crystals act as physical barrier which increases chain rigidity and thus the modulus. Semi-crystalline polymers also possess high strength because load-bearing capacity of polymer increases with increasing crystallinity, whereas elongation at break decreases with increasing crystallinity because crystals do not stretch. So, we learned that depending on polymer crystallinity, polymer mimic different properties. Crystalline phase tend to make polymers strong, while amorphous phase is more effective in providing flexibility. Thank you very much for watching the video. If you have any questions or suggestions, please comment below. If you like the video, please subscribe to our channel Polymer World. Thank you.